welcome to another module in this massive open online course on probability and random variables for wireless communications. In the previous module, we have looked at an important quantity, that is the power spectral density of the random process xt, which is basically the Fourier transform of the autocorrelation function Rxx tau. Now let us look at an application of this concept of power spectral density in the context of wireless communication or in the context of a communication system. So let us look at an application of power spectral density. Let us look at an application of power spectral density, which we have denoted by the abbreviation P of S. So we consider a wireless signal xt, that is a random signal, which is naturally therefore random process since it is a function of time. Consider a wireless signal xt with autocorrelation function Rxx of tau, which is given as Rxx of tau is 1 over 2a e to the power of minus a magnitude of tau, right. So, and further we are given that this parameter a is, let us say, equal to 5 kilohertz. A is given to be 5 kilohertz. So what we have a wireless signal x of t, which is a random signal. The random signal is naturally a random process because it is a random variable as a function of time. We are also being told that its autocorrelation Rxx tau is 1 over 2a e raised to minus a magnitude of tau, where the parameter a is 5 kilohertz. Now e raised to magnitude of tau is basically a decaying exponential with respect to tau on both sides of tau, that is for positive tau and negative tau, because it is e raised to the magnitude of tau. It looks something like this. If I have to plot this, it is a decaying exponential. It looks something like, at obviously tau equal to 0, this is basically 1 over 2a. So at tau equal to 0, this is basically 1 over 2a, and this is basically your, this whole thing is basically your 1 over 2a e raised to minus magnitude of a, e raised to minus a magnitude of tau. And now we can ask a couple of questions. For instance, for this signal, what is the power? For this random signal, what is the power? For this wireless communication signal, what is the power? What is the power spectral density? What is the power spectral density for the given signal xt? Further, another interesting aspect, further, from the power spectral density, calculate the bandwidth required for which contains bandwidth required which contains 90% of the signal power. So we are being asked, that is basically we are given a random signal x of t with power spy with autocorrelation function Rxx tau is 1 over 2a e raised to minus a magnitude of tau. We are asked what is the power of the random signal, right? What is the average power of the random signal? what is the power spectral density of this random signal xt, and more importantly what is the bandwidth required to transmit this signal, and not just any bandwidth, what is the bandwidth required to transmit this signal which contains 90% of the signal power, on an average which contains 90% of the signal. And this is an important quantity for wireless communication, because we have to decide a bandwidth for transmission of the signal, and the transmitted signal cannot have an undue or cannot have a large amount of power outside the band of transmission. So therefore, most of the signal energy has to be restricted to a particular band of transmission. Therefore, we are asking the question, what is the bandwidth of the, what is the bandwidth that is required which contains 90% of the signal power, so that only 10% of the signal power or a small fraction of this signal power is basically radiated outside of this band. And this is important because one has to restrict a majority of the wireless signal power to a certain band. Now let us look at the solution for this. Let us look at the solution for this. And the first part is simple, because the power is expected x t square, which is equal to r x x of 0, which is equal to 1 over 2 a e raised to minus a magnitude of 0. This quantity is basically 1. So the power of the signal is 1 over 2a. So basically from the autocorrelation function, what we get is that the power of the signal, power of the message signal, the power of the signal is 1 over 2a. So basically how do we obtain the power of the signal xt? Remember, Rxx0, that is autocorrelation corresponding to the delay tau equal to 0 gives the average power of the signal. By setting tau equal to 0, we have obtained that the power of this signal is basically 1 over 2a. Okay. Next we are asked what is the power spectral density of this signal, that is the power spectral density. Remember, the power spectral density is the Fourier transform of the autocorrelation function. Therefore, the power spectral density can be obtained as equals r xx of tau, which is equal to basic power spectral density is, I am sorry, this is S xx of f, which is basically equal to the integral of which is basically integral to integral of, that is a Fourier transform of the autocorrelation function, that is integral r xx of tau e raised to minus j 2 pi f tau d tau, and we know the expression for the autocorrelation function. Therefore, this is equal to minus infinity to infinity 1 over 2a e raised to minus a magnitude of tau e raised to minus j 2 pi f tau d tau. Now, since the magnitude is basically, I can split this into, since I am looking at the modulus of tau, I can basically split this into two integrals. This is basically 1 over 2a integral of 0 to infinity, that is for tau positive I have magnitude of tau, that is modulus of tau is equal to tau. So, this is e to the power of minus a tau e to the power of minus j 2 pi f tau, plus another integral from 0 to minus infinity to 0, that is negative tau, in which modulus of tau is minus tau. So, minus infinity to 0 e to the power of a tau e to the power of j minus j 2 pi f tau d tau. Okay. So, I have split this into two integrals, and now I can write the first integral as 1 over 2a. I can write the first integral as 1 over 2a integral 0 to infinity e to the power of minus a plus j 2 pi f into tau d tau plus 1 over 2a integral from minus infinity to 0 e raised to a minus j 2 pi f times tau d tau, and I can evaluate each of these integrals separately. The first integral is basically reduces to 1 over a minus of 1 over a plus j 2 pi f e to the power of minus a plus j 2 pi f tau evaluated between the limits 0 to infinity plus 1 over 2a e to the power of a minus j 2 pi f divided by a minus j 2 pi f tau between the limits 0 to infinity. And now therefore, you can see that this is basically 1 over 2a. On substituting the limits, you can see this is 1 over 2a times 1 over a plus j 2 pi f plus 1 over a minus j 2 pi f, which is basically equal to, this is basically equal to 1 over 2a times 2a divided by a square plus 4 pi square f square, which is basically equal to 1 over a square plus 4 pi square f square, and this is therefore your power spectral density. This is therefore your power spectral density. We have derived the power spectral density for this random message signal xt with the autocorrelation 1 over 2a e raised to minus a magnitude of t. We have shown that the power spectral density, which is basically the Fourier transform of the autocorrelation function, that is given as 1 over a square plus 4 pi square f square. This is the power spectral density Sxxf of the message signal. Okay. So, this is the power spectral density of the message signal under consideration. This is our power spectral . This is the power spectral density, and now you can see this power spectral density. If you can see this power spectral density Sxx of f equals 1 over a square by 4 pi square f square. If I plot this power spectral density at f equal to 0, it is 1 over, it is equal to 1 over a square, and if I plot this power spectral density, it is going to look something like, this. If I plot it at x equal to, it is 1 over a square at f equal to 0, this is the frequency, this is the power spectral density Sxx f of the wireless signal under consideration, which means if you look at the frequency band, the power spectral density is non-zero over the entire frequency band. The power spectral density is 1 over a square plus 4 pi square f square. At f equal to 0, it is basically 1 over a square, and basically it decays towards 0 at f equal to infinity, and f equal to minus infinity it becomes 0, but it is otherwise basically present over the entire frequency band, which means if I have to transmit all the power in the signal, I have to utilize the entire frequency band, which is not possible because the bandwidth of frequency transmission in a communication system or a wireless communication system is limited, right. So, we cannot have an infinite frequency bandwidth, a frequency band of infinite bandwidth available for transmission of the signal. Therefore, this leads to the next question, that is, we would like to find the bandwidth that is required for transmission of 90% of the signal energy. So, the next question is very interesting. What is the bandwidth? So, let us say I consider a bandwidth minus w comma w. So, what is the band minus w to w that contains, so what is the band or bandwidth that contains 90% of the signal energy, and that is very simple. The energy present in a, consider, let the bandwidth, consider band minus w comma w. We said the energy of the signal in this band, that is energy of xt in this band in the band minus w to w is basically the integral of the power spectral density. So, this energy is basically integral of the power spectral density, that is area under power spectral density in minus w comma w. That is, the energy contained in the signal in this band minus w to w is the area under power spectral density in minus w to w, and this has to be 90% of the total energy. Remember, we found earlier that the total energy is 1 over 2a. Therefore, this energy in the band minus w to w has to be 90% of 1 over 2a. So, this energy has to be equal to 90% or 90 over 100 times 1 over 2a, and therefore, that gives me basically that 0.9 over 2a is equal to minus w to w 1 over a square, that is power spectral density a square plus 4 pi f square times df. And now, I am going to manipulate this expression on the right, this integral on the right. I am going to bring out this factor 1 over 4 pi square integral minus w to w 1 over f square plus a square by 4 pi square df, which is in turn equal to, now I can write this as basically 1 over 4 pi square times 2 pi over a times, this is a standard integral, that is tan inverse of f divided by a over 2 pi evaluated between the limits minus w to w, which is equal to 1 over 2 pi a, and on the left of course, we have 0.9 divided by 2a, that is the 90% of energy, 1 over 2 pi a times twice tan inverse w by a by 2 pi, and therefore, we have 0.9 over 2a equals 1 over 2 pi a into twice tan inverse 2 pi w by a, which implies, now first this 2's cancel, therefore, I have tan inverse 2 pi w over a should be equal to, taking this pi a onto the right side, I have this is equal to 0.9 times pi by 2, which basically implies, taking the tan inverse to the right, that becomes the tan 2 pi w by a equals tan of 0.9 pi by 2, which is equal to 0.9 pi by 2, which is equal to 6.3138. So, I have 2 pi w by a, 2 pi w by a, where the minus w to w is the required bandwidth, 2 pi w by a is equal to 6.3138. 6.38, and now I can find W as W equals A over 2 pi times 6.3138, which is equal to 6.38 by 3138 divided by 2 pi, that is equal to 1.005 times A. Therefore, the required bandwidth, which contains 90% of the signal power, bandwidth required bandwidth which contains 90% of the signal power is minus W to W, that is minus 1.005 A to 1.005 A. So, required bandwidth which contains 90%. So, now what have we done? We have evaluated the power over this bandwidth minus W to W, and we said it has to contain 90% of this signal power, and from that equation we have derived that this capital W has to be equal to 1.005 times the parameter A. Therefore, the required bandwidth for transmission of this wireless signal which contains 90% of the power, 90% of the signal power is minus 1.005 A, that is minus W, to plus 1.005 A, that is plus W, and 1.005 is approximately equal to 1. So, this I can say this is approximately equal to minus A to A, and remember we were given earlier that A is 5 kilohertz. So, this is basically you are minus 5 kilohertz to 5 kilohertz baseband signal bandwidth. So, one can say the total bandwidth, the pass band signal bandwidth after modulation by the carrier the pass band bandwidth required is twice A, which is 10 kilohertz. And this is a very interesting problem. What we are seeing is basically, although the power spectral density is spread over the infinite frequency band, that is from minus infinity to infinity, it has an infinite spread or infinite support. However, most of the signal energy is contained in a bandwidth from minus 5 kilohertz to 5 kilohertz. How much is the band? How much is the signal energy? That is 90% of that signal energy, that is a dominant fraction, is contained in this band, that is from minus A to plus A, which is minus 5 kilohertz to plus 5 kilohertz. Therefore, the spectral bandwidth, the band that is required to transmit a majority or this 90% of the signal energy is basically, as we are seeing here, that is basically this is 10 kilohertz, although so this contains this 10 kilohertz, this contains, so this basically contains 90% of this basically contains 90% of the signal energy, which is a very interesting result, because now we have derived what is the bandwidth required for the transmission of a wireless signal, such that even though it requires, ideally it requires an infinite bandwidth, practically for 90% of the signal energy it only requires a bandwidth of about 10 kilohertz, a pass band bandwidth of 10 kilohertz. So, this is an interesting example of a power spectral density, application of power spectral density in the context of communication and wireless communication systems. That is, given the autocorrelation function, we have derived what is the power of the message signal, the average power, and we have derived what is the power spectral density, that is 1 over A square plus 4 pi square f square, which is the Fourier transform of the autocorrelation function, and also interestingly we have derived the band that is required for transmission of 90% of the signal energy, which we have said is basically a pass band bandwidth of 10 kilohertz. Right. So, this example illustrates application of this very important quantity of power spectral density in the context of wide and stationary signals, which arise very frequently in the analysis of communication systems and especially wireless communication systems. So, we will stop this module here. Thank you very much.